A chatbot is a short trip. You ask a question, it answers, and the transaction ends. An autonomous agent leaves the meter running for hours. Every thought, file read, and loop clicks the meter up. In one instance, a company provided its engineers with an autonomous coding agent but forgot to set a usage limit. The resulting invoice was $500 million. Uber exhausted its entire annual AI coding budget by April. Priceline saw routine internal tooling renewals return with price tags 5 times higher than the previous year. Small-scale operations are just as vulnerable. A simple 4-agent loop left running unsupervised for 11 days burned $47,000. This chart compares a standard corporate AI baseline against the usage of a single healthcare enterprise. They consumed 1 trillion tokens over 6 months, resulting in $6 million in unplanned API fees. The defining constraint on autonomous systems is the financial cost of allowing the model to think. Modern models have the capability to do the work, but every step of the reasoning process requires tokens. Every token consumed carries a fixed price, making every computational step a financial transaction. An autonomous agent functions by rereading its own history to decide its next action. The system resends its entire accumulated context at every turn. Step 90 pays to reread the 89 steps that came before it. Because of this rereading, cost compounds rather than adds. This makes the later stages of a task significantly more expensive than the first, even if the complexity of the thought remains the same. Gartner research highlights how this mechanic scales across an enterprise. Agentic tasks typically demand 5 to 30 times the token volume of a single standard model turn. The result is an 18-fold rise in per-developer token consumption in under a year. The loop that makes an agent intelligent is the same mechanism that makes it expensive. Treating cost management as a back-end cleanup process happens too late to stop a runaway autonomous loop. We move cost into the loop itself, treating it as a real-time cognitive variable. By installing engineering levers directly inside, we reduce spending without degrading reasoning quality. This strategy exploits the 5 times price gap between high-end and entry-level models. We use Claude Opus 4.8 for heavy reasoning at $5 per million input tokens, while routing simpler tasks to Claude Haiku 4.5 at $1 per million. 3 of our levers, route, cache, and prune, cap the bill, while the 4th, budget, forces the agent to watch its own meter. These 3 levers turn a runaway Claude bill into a budget. Let's build them. Lever 1. Routing. To control your compute budget, you must stop sending every trivial thought to an expensive frontier model. In this system, we balance 2 models. Claude Haiku 4.5 is our baseline, and Claude Opus 4.8 is our premium option. The economic gap between them is massive. For the exact same volume of tokens, Haiku is roughly 5 times cheaper than Opus. Because of that price difference, routine work goes to Haiku. Tasks like basic classification, data extraction, formatting lists, and short factual lookups do not require a massive parameter count to execute perfectly. We reserve Opus strictly for complex work, where parameter count actually matters, specifically multi-step reasoning, writing code, and high-level system design. To manage this traffic automatically, we place a lightweight classifier right at the front door. It analyzes the incoming request and routes it, with the cheap model set as the strict default destination. The core philosophy here is simple. You spend a tiny fraction of a cent evaluating the task first, so you don't commit to a massive compute spend by accident. Tasks only escalate to Opus when the classifier flags the prompt as inherently difficult or returns a low confidence score. By keeping this strict default, the vast majority of routine traffic flows to Haiku, sharply cutting the overall API bill. Meanwhile, those rare, computationally heavy requests still receive the full reasoning quality of the frontier model. But this architecture introduces a specific engineering risk: overrouting. If you send a complex reasoning task to the cheap model to save money, and it silently fails or hallucinates an answer, the entire agent pipeline breaks down. You have traded a minor saving on an API call for a critical system failure. A wrong answer is far more expensive than a few extra tokens. To mitigate this, you must calibrate the classifier's confidence thresholds conservatively. When the system is unsure about a request, the only safe technical choice is to escalate to the frontier model. Lever 2 is caching. Stop paying the API to reread data that never changes. Most agent calls share what we call a stable prefix, a massive block of text at the start of the context window. This includes long system prompts, dense tool catalogs, and static knowledge bases. Anthropic provides a prompt caching feature that allows you to mark the exact end of this stable prefix using a parameter called cache control. The economics of this are highly favorable. The first API call writes the cache at a small premium, about 1.25 times the standard input price, but every subsequent call reads that stored cache for roughly 10% of the standard cost. Prefix caching relies on an identical text match, making it fragile. Inserting a dynamic timestamp or reordering your tool list will silently invalidate the entire cache match. The architectural solution is to place the highly volatile part, the user's actual prompt, completely after that cache breakpoint, ensuring the prefix remains perfectly intact. Strict prefix hygiene protects this discount. Managed correctly, you never pay full price to send your agent foundational instructions twice. This diagram outlines semantic caching, an evolution beyond exact text matching that can short-circuit the model API entirely. Instead of requiring identical phrasing, it uses cosine similarity to match incoming user queries based on their underlying intent and meaning. If one user asks about the refund window and another asks, "How long do I have to return this?" the system recognizes they mean the same thing and triggers the exact same stored answer. Let's look at the cache miss pathway at the bottom right. This is what happens when a query has no historical match in the database. On a miss, the system calls the model normally, pays the full API input price, generates the response, and then stores that resulting answer for future use. Now look at the cache hit pathway at the top right. This occurs when a new query successfully matches a previous intent. The economic outcome of a hit is absolute efficiency. 0 model tokens are consumed, bypassing the billing meter entirely. As shown in the bottom left panel, the primary risk of this setup in a production environment is cache staleness. If you cache a response that depends on live data or per-user permissions, a stale hit can accidentally serve one customer's private account state to another customer. Because a wrong cache hit is catastrophically worse than a simple miss, semantic caching must be restricted exclusively to stable, low-risk data. Lever 3 is pruning. You don't want to pay a genius model to read filler text. Deep into an autonomous agent run, the context window becomes severely bloated. It fills up with resolve errors and messy raw web page dumps from previous steps. Out of 10 pages of raw HTML data dumps, only a single sentence might actually be relevant to the next logical step. We handle this using a compressor module. We deploy a small, cheap model to actively read and score the value of those incoming tokens, stripping out the low-value filler. The physical effect is immediate. Stripping out the noise dynamically shrinks the total payload size by anywhere from 4 to 10 times. Crucially, this massive volume reduction occurs completely isolated from the expensive frontier model before it is ever invoked. Deploying cheap compute to clean up a messy context window is the ultimate defense for the frontier model's token limits and your billing meter. None of these 3 levers are theoretical concepts. The entire architecture is just a thin layer of plain Python wrapped directly around the standard Claude SDK. Here, you can see the logic that intercepts the request, checking the local semantic cache for exact repeats before doing anything else. Below that is the routing logic, clearly showing the cheap first default to Haiku, alongside the fallback trigger that escalates the task to Opus on low confidence. And we can see exactly where the cache control parameter is dynamically injected onto the end of the shared context prefix. By wrapping every single call in a telemetry function, you can meter exact token usage and dollar spend in real time, verifying your cost savings on a per-task basis. This entire Python decision layer is fully open source. You can find raw architecture in the neuralsca/foundations demos repository on GitHub. You can clone the repository today, input your own API keys, and run the pipeline locally to test the routing and caching behavior yourself. That is the architecture on paper. Now watch it run on real Claude. Watch the naive agent execute a standard workflow. The meter is always running, and this live terminal output captures an unoptimized request loop in real time. The inputs are standardized. The agent is referencing a shared knowledge base to answer a fixed queue of 7 distinct queries. In this first pass, the architecture defaults to maximum capability. Every single query is routed directly to the most expensive tier, Claude Opus 4.8. The structural flaw becomes apparent immediately. The system blindly packages and resends the entire knowledge base for every individual question in the queue. That means every transaction carries a redundant payload of approximately 14,900 input tokens, on top of the unique output tokens generated for each answer. Wasting computational power on static context forces the API utility meter to climb unsustainably fast. Tracking the real-time financial kilometry of this first pass, we can see that each individual query line is costing roughly 7.7 cents to execute. This chart visualizes the aggregated cost of the Pass 1 queue, bringing the execution price to over 54 cents. Expanding reveals the underlying math. The heavy payload is billed against the Opus price card of $5 per million input and $25 per million output. We have to evaluate that premium metric against the actual difficulty of the tasks. The current queue is populated almost entirely by simple, easily solvable retrieval queries. The system is paying top-tier reasoning prices for basic operational work. Relying exclusively on a frontier model creates an immediate financial bottleneck. Processing capability without architectural frugality simply cannot scale in a production environment. We can reset the telemetry audit to begin Pass 2, this time with a deliberate cost awareness layer activated. This logic tree evaluates task complexity upfront. Easy questions bypass the heavy model entirely, routing down to Claude Haiku. At $1 per million input tokens, Haiku operates at a fifth of the Opus baseline, completing identical work for a fraction of the price. The execution telemetry confirms that 4 of the 7 queries were intercepted and handled by Haiku, dropping the cost of those specific calls to mere fractions of a cent. The system still requires an escalation pathway. The queue contained one genuinely difficult design query, which the logic gate correctly identified and deliberately routed up to Claude Opus. Dynamic routing guarantees that an intelligent system only pays the premium reasoning price when the specific task strictly demands it. To address the secondary failure point, the shared knowledge base is cached to prevent the system from repeatedly paying for the same foundational context. This block represents Anthropic prompt caching. During the first Haiku call, the system executes a cache write operation, indexing exactly 10,931 tokens. For subsequent queries, the architecture shifts to a cache read state, referencing pre-indexed memory instead of processing raw text from scratch. Referencing this repeating context is now billed at approximately 1/10 the cost of a standard input token. Reviewing the API telemetry verifies the math. The heavy cache creation input tokens register only once, while the remaining calls trigger the heavily discounted cache read input tokens. Proper caching architecture takes an escalating contextual payload and converts it from a compounding liability into a negligible, one-time fixed cost. The final layer of inefficiency in the test queue comes from processing 2 identical questions in succession. The cost-aware layer utilizes local repetition suppression. When an exact repeat is detected, it is intercepted and answered entirely from local memory. The telemetry for those 2 repeating queries validates the approach: 0 tokens processed and precisely $0 spent. Aggregating the routing, the prompt caching, and the exact match suppression, the total amount saved becomes clear. This dual-bar meter compares the financial totals. Against the 54-cent baseline of Pass 1, Pass 2 completed the entire queue for just under 12 cents. That is a 78.3% cost reduction. The system dropped the Claude API bill by nearly 80%, while returning the exact same answers as the unoptimized pass. In operational reality, that precise 78% savings metric is highly dependent on the shape of your real-world traffic. The math fluctuates based on the ratio of simple, repetitive tasks versus genuinely difficult requests where Opus still earns its premium rate. Furthermore, optimization carries its own structural constraints. A stale cache, for example, is mathematically more expensive than a standard cache miss. These 4 icons map the hierarchy of system constraints. Because of cache and validation risks, safe levers like complexity routing must always be prioritized first. Route so you never overpay for easy work. Cache so you never pay twice. Prune so you drop dead weight. And budget so the agent weighs every single thought against its price. A true cost-aware agent objectively evaluates whether an answer is worth its computational price before it begins generating it. We have to build systems that can think, and then build systems that know exactly what their thinking costs. The meter is always running. The only question is whether your agent is the one watching it.